Hello, welcome to a video about superposition. Superposition is the net response caused by multiple stimuli. In terms of waves, multiple waves may be propagating through the same medium. If they're travelling in opposite directions towards each other, they'll pass through each other undisturbed, but the net displacement of the medium will be the sum of each wave's displacement. So in our picture here, we've got two waves that are travelling towards each other. When they meet, the medium is displaced as a sum of each wave's displacement. These waves pass through each other and then they'll just continue on their merry way. In stage 1 physics, you need to be able to use the principle of superposition of waves to explain a range of interference phenomena, including standing waves and beats. Interference is when waves undergo superposition and the resultant wave has an amplitude that is greater than or less than the amplitudes of the original waves. Constructive interference occurs when crests interfere with crests and when troughs interfere with troughs, and the resultant amplitude is greater than both original waves. So in our example over here, we've got two waves that are different amplitudes. They're travelling in opposite directions towards each other. When they meet, their amplitude, even though it's a bit irregular, is equal to the sum of both waves, and then they just continue on separate in their own directions. We've also got constructive interference occurring here. So this is when waves of the same amplitude and same frequency interact. The overall wave that results has the same frequency, but the amplitude is double the amplitude of both original waves, so they've just been added to each other. Destructive interference occurs when a crest overlaps with a trough and the resultant amplitude is less than both original waves. So here we've got a crest and a trough travelling towards each other. They're different in magnitude in terms of their amplitude, but when they interact, the overall result is like an amalgamation of both waves. And then, like with constructive interference, they'll just continue on their merry way. Over here, we've got two waves of equal frequency and equal amplitude, but the way that they're aligned is such that the crest of one wave aligns with the trough of another wave and vice versa. So when they interfere, the result is just like a zero displacement or a zero amplitude. An application of this is noise cancelling headphones, and they intend to minimise the amplitude of sound waves from the external environment. So a microphone on the headphones will detect external sounds, it will analyse this sound, and then the headphones will emit sound waves to destructively interfere with this external sound. Beats are periodic variations in amplitude of sound waves due to alternating regions of constructive and destructive interference. So the original waves might have nearly equal frequencies, but their frequencies will result in waves that in some sections align constructively and in some sections align destructively. So for example, in this section here, the waves are pretty much aligned, so the interference will be constructive, and this results in a sound wave of greater amplitude. Whereas here, the sound waves are interfering more destructively, so this results in like a zero section of the sound wave because the troughs and crests have cancelled each other out. So when you're listening to it, when you're interpreting it, is like the part or the section in between each beat that sounds a bit lower in volume. Standing waves form when two waves of the same amplitude and the same frequency travel in opposite directions towards each other. So the constructive and destructive interference ends up occurring at the same locations, and as a result, the wave appears to be standing in place. So an example of this is a vibrating string where waves will propagate along the string, and these waves will be reflected from the endpoint or the surface, and the reflected waves and the source waves will interfere with each other. Where destructive interference is occurring is called a node, so this is this section here, and where constructive interference is occurring is called an antinode. So this here is just one string, and this peak here will alternate with this trough here, and this peak here will alternate with this trough here. So it will seem like the wave is standing in place. The node here will remain in the same place. The antinode is a region of maximum displacement, and this occurs due to constructive interference. So node is destructive interference, antinode is constructive interference. Large amplitude standing waves form when the forced vibration, so forced vibration due to the hands vibrating up and down or oscillating up and down, when that is equal to the natural frequency of the string. Harmonics are resonant frequencies that are produced in vibrations of standing waves. So the frequencies that produce standing waves, or the frequencies of vibrations that produce standing waves. The first harmonic, or the fundamental frequency, is the lowest frequency that produces a standing wave. The second harmonic is the second lowest frequency that produces a standing wave, and so on. This is the rule that relates wavelength to the harmonic number, or the number of nodes in a wave. So if you imagine a wall here, and we've got a string on the wall, the first harmonic will have just one node at the wall, and its wavelength will actually extend beyond the wall. So this here is the length of the string. Its wavelength will be 2L, so 2 times the length of the string, on 1 because it's the first harmonic. So therefore its wavelength will be twice the length of the string. So if you imagine the string continuing through, that will be the wavelength of the first harmonic. The second harmonic will have 2 nodes, so one here and one here. The second harmonic, its wavelength will be equal to twice the length of the string divided by 2, so just the length of the string, so this length here will be the wavelength of the second harmonic, so on for the third, fourth and fifth harmonics. Harmonics are produced whenever a vibrational frequency is an integer multiple of the fundamental frequency. So if you've got a fundamental frequency of 30 Hz, what is the frequency of the fifth harmonic? You'll just be multiplying 30 Hz by 5, so the frequency of the fifth harmonic will be 150 Hz. I'll just point out that wavelength is measured in meters, length of the string is measured in meters, and n is equal to the harmonic number or the number of nodes in a standing wave. Wave speed is dependent on string mass per length, and this quantity is represented using mu, which is the U with a tail on it, and it's also dependent on tension, which is represented just with a T. The rule that connects these is velocity is equal to the square root of tension divided by mass per length. The fundamental frequency of a string is dependent on string mass, string length, and string tension. And the rule for this is 1 on twice the length, or 1 divided by twice the length of the string, multiplied by the square root of the string's tension divided by the string's mass per unit length. So another way of writing this is that fundamental frequency is equal to 1 divided by twice the length multiplied by the wave speed. You can also just write this as wave speed divided by 2 times the length of the string. So as a worked example, you've got an 8 metre length of string with a mass of 6 grams. It's put under a tension of 140 newtons. Source and reflected waves propagate along its length when it is plucked. Calculate the speed of the source and reflected waves. So to do this, our rule for wave speed is V equals the square root of tension divided by mu. Mu is equal to mass divided by length, and in our situation here, mu is equal to 6 grams, which is 6 by 10 to the negative 3 kilos, divided by length, which is 0.8 meters. This overall is equal to 7.5 by 10 to the negative 3 kilograms per meter. We can then sub this back into our wave speed equation. So wave speed is equal to the square root of tension, which is 140 newtons, and then divided by 7.5 by 10 to the negative 3. Pop that all into your calculator and you'll end up with a wave speed of around 136.6 meters per second. That's how fast the source and the reflected waves are travelling. Next question wants us to calculate the wavelength of the first harmonic of a standing wave. The wavelength of the first harmonic will be equal to wavelength equals 2 by length of the wave on n. N is going to be equal to 1 because it's the first harmonic, and length of the string is 0.8 meters. So wavelength will be equal to 2 by 0.8 for our length divided by 1, and this will be equal to 1.6 meters. So that's the wavelength of the first harmonic. Now we've got a 1.2 meter length of string, and it has a mass per unit length of 7.8 by 10 to the negative 3 kilograms per meter, and it's put under a tension of 170 newtons, and we need to calculate the fundamental frequency of the string. So our rule for fundamental frequency is equal to 1 on 2L multiplied by the square root of T divided by mu, which is the mass per unit length. Our length is 1.2 meters. Our tension is 170 newtons, and 7.8 by 10 to the negative 3 kilograms per meters. So if we sub all of this into our equation, we'll get fundamental frequency is equal to 1 divided by 2 times 1.2, and then multiplied by the square root of 170 divided by 7.8 by 10 to the negative 3 kilograms per meter. And then if you pop all of that into your calculator, you'll end up with a fundamental frequency of 61.5 Hertz. So that is the fundamental frequency of the string. The next question wants you to calculate the speed of the transverse waves propagating along the length of the string. So for this, our speed equation is tension, square root of tension divided by mu, which is our mass per unit length. We know our mass per unit length, just to reiterate, is 7.8 by 10 to the negative 3, and we know our tension is 170 newtons. Mass per unit length is measured in kilograms per meters. So sub all of this into our equation. Velocity is equal to the square root of 170 newtons divided by 7.8 by 10 to the negative 3 kilograms per meters, and that in your calculator will end up being 147.6 meters per second. So that's the velocity of the transverse waves propagating along this length of string.